Number 11, we're asked to consider a circuit where the left half cell is prepared by dipping a platinum wire, so it's solid platinum, in a beaker that contains equal molar mixture of chrome 2, and that is aqueous, and chrome 3. So when we go to write our line notation, we put a comma between our chromium 2 and chromium 3. We do need to have the phases there. They are both aqueous. Then we're going to have our two lines. That indicates our salt bridge. Now, the right half cell is going to contain a thallium rod, so that will be my other anode, and immersed in a 1 molar Ti1+, and that is aqueous. Put a line between here. Remember, this single line shows a phase change, and the double line shows the salt bridge. We're told that the chromium is on the left half of the cell, and the thallium, I put Ti, the thallium is on the right half of the cell. Now, the left half of the cell is the anode, and the anode contains oxidation. The right half of the cell is the cathode, and the cathode is where reduction occurs. So if we're going to find the potential of each half cell, here's my anode, here's my cathode, I need to look up what these standard reduction potentials are. And I have inserted, this is actually images from Harris's 5th edition. This is Appendix C, because I figured, or I learned by trying to do this problem, that what I had posted here from the OER text just wasn't thorough enough. So you do get Harris's Appendix C here. So I'm looking for chromium going from 2 to 3. And the elements are in alphabetical order by name. So chromium 2 to 3 is going to be this one, negative 0.42. And the thallium then, scroll down till I get to T. There's silver. I'm looking for, there we go, thallium 1 to solid is a negative 0.336, and these are volts. So in order to find the potential, so that's each half cell, calculate the cell voltage. Well, the E of the cell is going to be equal to the E of the cathode as a reduction minus E of the anode. So in this case then, we have a negative 0.336 volts minus a negative 0.42 volts. And I didn't have to do anything Nernstian because I am told we have an equal molar mixture here. So this ratio would end up being 1, and the log of 1 is 0. So it's just the reported value. And at 1 molar, this is standard, the standard conditions. So we don't have anything Nernstian to do here. So the E of the cell is just going to be 0.08 little 4 over there, and this is positive. So C, we're asked to draw a diagram like 14.8. Well, in order to do that, we need to know what 14.8 or 14-8 looks like. This is what 14-8 looks like. So in order to draw a diagram like that, on the left side here, I would have platinum, Cr3 plus, Cr2 plus. I would have my E equal negative 0.42 volts. I would have a scale down here. And I'm not going to have a 0, but I'm going to have my, give it little hash marks. And let's call this 0.43, 0.42, etc. And then my electrons are going to flow this way from chromium 2 to thallium plus, and then my hash marks, wherever my hash marks end up, I need it to end up at E equals negative 0.336 volts. And I would put, again with the titanium, like this. So this would be negative 0.34, 0.35, negative 0.33. So something on the order of this is what they're looking for. And D, write the spontaneous net cell reaction. So we would have thallium, chromium, and the thallium is being reduced to solid thallium, and the chromium is being oxidized to chrome 3. So that's what we're looking for in a question like number 11. Number 12, we're asked to consider this cell. We have platinum, we have hydrogen at a particular pH, and then it looks like we have the calomel electrode, standard electrode. So for A, we're going to write the reduction reaction and the Nernst equation for each half cell and find each half cell potential. So we will start the right half of the cell. The right half is the cathode, and that's going to be Hg2Cl2 solid plus 2 electrons in equilibrium with 2 Hg liquid plus 2 Cl minus. And then the E for this reaction, get rid of this, is a positive 0.268. And that is volts. And the left half, the left is the anode, and that is where oxidation is going to occur. And that's going to be 2H plus 2 electrons, H2 gas. So I've written it as a reduction because when I go to look it up, the E naught is in the reduction form. So the right half, the cathode, the Nernstian equation there, the E of the plus, is going to be 0.268 minus, and then we have our constant, 0.05916 divided by N, the number of electrons that are transferred, so we have a 2, log of the concentration of the products over the reactants. Now, because we have a liquid and a solid, remember they don't end up in your Q expression, we only have the concentration of the chlorine, and it's going to be squared. And the reason it's squared is because of our coefficient. So that's going to be our cathode reaction. So E plus, the concentration of the chlorine, I'm looking back up here, it's given to us as 0.2. So that's what I'm going to fill in here. And then when I do that calculation, I get the E of the cathode is 0.3094 volts. Now for the anode on the left side, E of the minus, we start with the standard reduction potential that we were given, 0. And then we're going to subtract our constant divided by the number of electrons in that reaction times the log of the concentration of the pressure of the products over the concentration of the reactants squared. Again, it's squared because of the stoichiometry. So how are we going to find the concentration of the hydrogen ion? Well, remember what pH means. pH is the negative log of the concentration of the hydrogen ion. So if I have the pH, I can find that concentration. And the pH is given as 2.54. So the concentration of the hydrogen ion is 10 raised to the negative 2.54. So the pressure is given to me here as 0.100 bar, and that's our standard unit. So now all we have to do is put this in the calculator and solve that the E of the left half of the cell is a negative 0.1207 volts. So now we can find the E of the cell. Did we? Yeah, we are asked for the E of the cell. I'm going to skip the diagram. I don't like the diagrams. So we're going to find the E of the cell for the net reaction. Remember, the E of the cell is going to be the E of the cathode minus the E of the anode. So I have the cathode minus the anode, and that's going to yield a positive 0.430 volts. Number 14. Now, I like number 14 for a couple of reasons. So the point is, you're not going to find each of these things in Appendix C. You have to figure out which half reactions will yield this overall. So we have our copper solid, and it is going to be oxidized because it can't be reduced, and it's going to be oxidized to copper 1. So I must have 1 electron here. Then I also have my copper 2, my aqueous copper 2, and it's going to be reduced. It's going to be reduced to copper 1 because that's all I have on my product side. So I know that these are the equations I'm looking for. So I go back over here and I'm looking for copper. Copper. So the first equation given is actually the first equation I need, and that reduction is 0.518. And the second equation that I have written down here, going from 2 to 1, is the third equation on my list, 0.161. So this top equation, this is oxidation. So this is my anode, and this one down here, this is my cathode. This is reduction. And the E of the cell is going to be the E of the cathode, the E naught in this case, minus the E naught of the anode when they're written as reduction potentials. So I'm going to take 0.161 and I'm going to subtract 0.518 volts. So the E of my cell for this particular cell is going to be a negative 0.357 volts. So the K is going to be 10 raised to, well, the exponent is n E naught over 0.05916. So the n for this is 1. So the E naught that I just figured out is a negative 0.357. And then make sure you're entering this into your calculator correctly. You should get a K value is equal to 9.2 times 10 to the negative 7. On my calculator, I have a 10 and then a box, and that is above my log button, okay? And I need to press my second key, or it could be shift, and then log, and then what I get in my display is 10, and then I get a caret, and then it's waiting for the rest. Put in parentheses this whole thing. So negative 0.357 divided by 0.05916. Close the parentheses and hit enter or equals, and you should be able to get this K value for A. For B, we're going to do something very similar. We need to find what's being oxidized, what's being reduced here. So I have my F, which starts as a 0, and then it becomes F2O, that's a +1. So I also have F, which becomes, I can't write an F for some reason, F minus, and 2 of those. So remember from our balancing, first we're looking for atoms other than oxygen and hydrogen. You can balance that way, or you can come over here to your half reactions. Look for fluorine. For some reason, I can't spell fluorine. And we're given 2 half reactions. So we have F2 plus 2 electrons is 2F minus. And that has a standard reduction potential of 2.890. And then our other equation up here, F2O gas plus 2H plus 4 electrons reacts to form 2F minus plus water. So I had my first equation wrong. So doing it this way is a great double check. And that standard reduction potential is 2.168 volts. So now we need to figure out which is the anode, which is the cathode, and then find the E of the cell, because the E of the cell is going to be the E of the cathode minus the E of the anode. I can't spell anode either. So this equation is obviously going to be our reduction. That makes this equation our oxidation. Remember, oxidation is loss. Reduction is gain. We are gaining here. We are losing here. So the E of the cathode is 2.890 volts minus the E of the anode, 2.168 volts, which gives us an E of the cell of 0.722 volts. So now I can calculate my K, and my K is going to be a 10 raised to the N E naught over our constant 0.05916. The N now is going to be 4. We're transferring 4 electrons. Even though there are 2 electrons here, what we would end up doing when we go to balance this is multiplying everything through by 2 in order to get our electrons to balance. So this N is 4. The E naught that I just calculated is 0.722. And when you calculate this K, you should end up with something on the order of 7 times 10 to the 48th. So that is definitely a strong reaction, definitely spontaneous.